Okay, next we will continue with step 3, which is digestion. So the digestion is quantitative analysis, which refer to the coagulation of a precipitate into a filterable form. So it means that when you put the two solution together, the analyte of interest and the precipitating agent, you have to let it digest in order for it to form precipitate, okay, in which later on can be filtered out. So the formation of the precipitate through coagulation is the process where the colloidal particles lump together in order to form larger particles. So remember, I have mentioned we want large particle through particle growth, not nucleation. Okay, so let us look at one example here. Silver nitrate and sodium chloride. In this case, sodium chloride is the precipitating agent. Okay, so the analyte of interest is silver here. Okay, so react with precipitating agent sodium chloride to form solid silver chloride. Okay, so this silver chloride tends to form colloidal or amorphous type of precipitate, and sodium nitrate is the remaining solution, which can be filtered out during the filtration step. Now there are two types of colloid, okay, either hydrophilic colloid or hydrophobic colloid. Hydrophilic means affinity towards water. Hydrophobic is dislike water. So ini suka air, ini tak suka air. So hydrophilic colloid will have strong affinity for water, and a solution of hydrophilic colloid is viscous and is called gel, whereas hydrophobic colloid little attraction for water, and the solution of this type of colloid is called sol. Now there are two common approach for a colloid to coagulate, okay, which are heating and adding electrolyte to solution. Okay, so when we heat the colloid while stirring, okay, this will significantly decrease the number of adsorbed ion per particle, and therefore this process will reduce the size of the primary adsorption layer, so making it easier for the particle to approach each other. Now what does this mean here? So go back to the reaction between silver nitrate and sodium chloride just now. Okay, in order to form silver chloride solid. Now, the formation of this silver chloride is due to these ions here. Okay, so therefore during the coagulation process, you will have, let's say this is silver, this is chloride, this is silver, this is chloride, this is silver, this is chloride ion. Okay, okay, so therefore during this formation of this solid in the solution, it's not just silver and chloride, okay, there are also presence of ions due to the solution used. For example, we have nitrate, we have sodium, we have H plus from water used to prepare these two solutions here. Okay, OH. Okay, so due to this reason, okay, there will be a formation of primary adsorption layer. Okay, this primary adsorption layer normally will have silver on the surface. Means, okay, so this is the the precipitate just now, and on this surface of this precipitate here, okay, there are primary adsorption layer made of the silver ion just now, because this is in excess, okay, because this one act as a precipitating agent, so that's why normally it's in excess. So you have this on the surface, okay, silver plus, okay. So due to this primary adsorption layer saturated on the surface, how is the particle going to grow in size? Okay, because it has to be alternate silver chloride. When there's too much silver, so very difficult for the chloride to approach. So therefore, when we heat this while stirring during the formation of precipitate, we can reduce this primary adsorption layer. So when we reduce this layer here, easy for the particle to approach each other and grow in size. The next one is increase the concentration of the ions responsible for the counter layer in the solution. So counter layer means the secondary layer. Okay, just now we have the precipitate here, right, in the bulb. Okay, so let's say this is the precipitate, and this is the primary layer composed of the silver ions, and we have the secondary layer, okay, or the counter layer. So this counter layer will have other ions like the nitrate, like the OH, okay, because this is positive just now, so means it's attract the negative ions. So we have the nitrate here, okay, nitrate and OH, okay. So an unrelated non-interfacing ionic compound can be added. Interfering ionic compound can be added to the solution. So this will reduce the volume of solution that contains sufficient ion of opposite charge to neutralize the particle and thus decrease the thickness of the counter layer. So this one will reduce, okay. So therefore a smaller structure form. After digestion, some of this primary layer must be washed away for quantitative result to be achieved. So means the remaining primary layer left behind can be removed through washing steps in the following step later on. Okay. So step 4 is filtration. This is where we separate the precipitate form from the remaining aqueous solution, okay, using either filter paper or any filtering crucible. So of course the most common filtering medium is filter paper, and it is cellulose based, okay, and these cellulose based filter paper are classified according to its filtering speed, its size, and its ash content upon ignition. Precipitate tend to carry down from the solution other constituents which are normally soluble, which cause contamination to the precipitate, and this process of contamination we call them co-precipitation. Okay, co-precipitation is undesirable because we only want the precipitate. Okay, co-precipitation is considered contamination. Now, where is this source of co-precipitation? Okay, the source of co-precipitation comes from either occlusion, inclusion, surface adsorption, post-precipitation, or mixed crystal formation, or in other words, is isomorphous replacement. Now let us look in detail of each of these co-precipitation. So what is inclusion? Inclusion is rapid crystal growth which traps some constituents of the precipitation medium. For example, ions of similar size and charge in the crystal structure. Okay, so this is how precipitate. Okay, during the formation of precipitate, especially rapid formation, it has the tendency of trapping ions which are not supposed to be in the precipitate, but it has similar in term of size and charge of the precipitate, like in this case here. Okay, so it trap together. Okay, so these are called inclusion. Okay, so this normally come from the secondary layer or the counter layer. Now, what is occlusion? Occlusion is when the precipitate rapidly grow in size, it has the tendency to trap a pocket of solution. Okay, because it grow too fast. Okay, the aqua solution, okay, is trapped, okay, in the structure of the precipitate. Okay, we can remove the solvent, remaining solvent, but the trapped ion here will remain even after drying. So that is occlusion. So the difference between inclusion and occlusion, inclusion are randomly distributed because due to the structure here, size, in terms of its size just now, similar size. But occlusion is localized. Okay, it's in the interior part of the precipitate. So that's the difference between inclusion and occlusion. So how to prevent occlusion and inclusion impurities? Occluded or included impurities cannot be removed simply by washing. So the best way is to slow things down. Means we are slowing down the precipitation process. In this case, by using dilute warm solutions during the precipitation stage, step 2, to give impurities time to leave and to help break up the pockets, especially the occluded impurities. Digestion may help, but not completely effective. Another way is purification by reprecipitation. Means we redissolve back the precipitate and let it precipitate out again. Okay, by purification technique. This is effective, but it is time consuming because we have to dissolve back the precipitate and then let it crystallize out again. The third type of impurities is surface adsorption, and this is the most common form of contamination. This surface adsorption impurities is similar like inclusion, just that it occurs only on the surface of precipitate. So therefore, to minimize surface adsorption, digestion is preferable because it will reduce the surface area. So when the surface area is reduced, then the available space for adsorption will also be reduced. Another way is washing. Okay, because it only occurs on the surface, it can be removed by washing. For example, if you look in this figure here, adsorption of nitrate ion on the precipitation of barium sulfate. So this is a barium sulfate precipitate. Okay, and then this is nitrate ion. Okay, nitrate ion. So it can absorb on the surface because this is negatively charged, so it can attract to the positive area of the precipitate. Okay, so this can be removed through washing. Okay, so this figure here shows the precipitate of sodium silver chloride. Okay, silver chloride. So the darkened circle is silver ions, whereas the gray area is chloride ion. So um, if you look carefully in the bark, okay, in the bark, for example here, silver is surrounded by 6 chloride ion. Okay, so 1, 2, 3, 4, 5, 6. Okay, 6 chloride ion. So it's fully occupied. However, on the surface, okay, on the surface here, okay, the silver ion is only surrounded by 4 chloride ion. So 1, 2, 3, 4. Only 4. So it has available two sites for surface adsorption to attach to it. Okay. The next type of impurities is post precipitations. Sometimes when the precipitate is allowed to stand in the mother liquor, okay, a second substance will slowly form a precipitate with the precipitating agent. Means the digestion process is taking too long. So if it's too long, it has the tendency of forming another precipitate, which is not the precipitate of interest. Okay, this is called post precipitation. Okay, for example, copper sulfide will precipitate in acid solution in the presence of zinc 2 plus ion. Okay, but eventually zinc sulfide will also precipitate due to the presence of sulfide also in the solution. Okay, so this is the post precipitation, the impurities. So how to minimize post precipitation? We can only carefully control the solution condition. Okay, so means we have to mask the interferent using a complexing agent so that we can prevent the precipitation. So we put another solution that can mask this zinc from precipitating out, forming zinc sulfide, so that this zinc will remain in solution form. So that solution is called complexing agent. So the last type of impurities is mixed crystal formation or isomorphous replacement. Okay, if you see the condition for mixed crystal formation is more or less like inclusion. Okay, so if similar ion with the same charge and size within 5%, okay, 5% of the analyte ion are present, they can replace the analyte ion in the crystal lattice. For example, precipitation of magnesium as magnesium ammonium phosphate. Okay, potassium has the almost the same ionic size as ammonium, so therefore it can replace to form magnesium for potassium phosphate instead of magnesium ammonium phosphate. Okay, this one, this and this have similar in terms of size, so this can form also. Okay, besides this. Okay, once impurities of mixed crystal formation has been formed, it cannot be removed. The only choice to remove this type of interference is before the precipitation process even begin, means before the step 2. Okay, so means we have to select a different reagent so that this kind of precipitate will not form. Okay, so avoid using reagent which having similar ionic size as the intended precipitate. Okay, step 5 is washing. So after precipitate has been formed, it undergoes filtration. So after filtration, it is crucial to wash the precipitate, especially to remove adsorbed species like surface adsorption impurities. Okay, this will add to the unnecessary weight of the precipitate. Okay, so some of the primary electric layer, okay, um, the primary adsorption layer must be washed away, okay, so that we get quantitative results. The disadvantage of washing is that peptization may occur. Okay, what is peptization? Okay, so let us talk back on discuss back on the silver chloride formation of precipitate. So we have the silver chloride precipitate here. Okay, so chloride absorbs on the particle, especially it is in excess. So I mentioned about this regarding the primary adsorption layer. Okay, so this is the chloride ion. Okay, so when it's in excess, it form primary layer. Okay, so once prime layer has been formed, counter layer also form, or the secondary adsorption layer will form. So this is the counter layer, okay, which attract to the negative chloride ion. So means the positive ions is the counter ion layer. So these will neutral, okay, neutralize the particle, okay. Um, so therefore, it avoid the formation of a more bigger um, precipitate. Okay, so washing with water would dilute the counter layer. Okay, so we use water as washing solution. Okay, would dilute this counter layer. Okay, and also the primary layer. So therefore, this leads to the revert uh, to the colloidal state. Okay, means peptization occur, breaking up of the particles. So here we have the silver chloride solid. So when it undergo washing with water, okay, it will form colloid state. Okay, so breaking of the silver chloride solid precipitate. So how to prevent peptization? Okay, instead of using water, we use volatile electrolyte. Okay, so washing with a solution of a volatile electrolyte will prevent peptization. Okay, and these volatile electrolyte uh, can be removed during the heating step. Okay, um, followed after washing. Okay, for example, silver chloride just now, instead of washing using water, we wash using hydrochloric acid. And then during the drying process of the precipitate at 110 degrees Celsius, it will remove this hydrochloric acid solution. So this is the figure showing the difference between peptization and also coagulation. Okay, so this is peptization. Okay, we have freshly precipitate of iron hydroxide, the hydroxide. So when we wash using iron trichloride solution, due to the similar of um, ion used in the washing solution, it will peptize the precipitate to form a colloidal particle of iron trihydroxide instead. Okay, so this figure here is showing coagulation. So at pH 5, okay, adding electrolyte with the ion oppositely charged to the ion of the solution will leads to a bigger precipitate. Okay, this is humic acid, okay, at pH 5, and this is humic acid at neutral condition. Okay, so you see the precipitate coagulate, okay, to form a bigger precipitate due to the oppositely charged ion. Okay, so this is the summary showing the difference between peptization and also coagulation. Okay, step 6 is drying and igniting. Okay, so the purpose of drying means heating at about 120 to 150 degrees Celsius in oven, or ignition in a muffle furnace at even a higher temperature ranging from 600 to 1200 degrees Celsius, okay, to get material exact non-chemical structure so that the amount of the analyte can be quantified. So the precipitate must be in suitable form for weighing. So I have mentioned in my earlier lecture, okay, precipitate must be dried, and the dry precipitate has to be at constant weight. Otherwise, it is to undergo ignition to convert into a more measurable weighing form. So many precipitate contain varying amount of water and adsorb electrolyte from the washing solution. Okay, so we heat or we dry the precipitate at 110 to 120 degrees Celsius for 1 to 2 hours. Okay, and we must obtain stable mass measurement for the dried precipitate. Otherwise, it has to undergo ignition. Okay. Okay, this graph show um, different precipitate, okay, dried at different temperature. Note that silver chloride undergo drying at 110 to 120 degrees Celsius, in which a stable mass can be obtained. However, for aluminum trioxide um, uh, with presence of water, okay, it can be monohydrate, dihydrate, pentahydrate, and so on, okay, depending on the X value. Okay, this one cannot dry at a constant weight, therefore it has to be ignite, okay, ignite to a very high temperature so that it will convert to a more measurable form. So in this case, aluminium trioxide is dried or ignite to temperature of more than 1000, then we get a stable mass, okay, for aluminium trioxide. This shows calcium oxalate monohydrate. Okay, I have discussed this in my earlier lecture also. So calcium oxalate monohydrate, okay, has to be converted through drying and also igniting so that it will form a more measurable form of the analyte of interest, in which calcium. Okay, so drying it up to 200 or plus degrees Celsius, okay, will reduce the weight. So it has to be dried at even higher temperature from 200 to 400, and when it reach about 400, the mass change also. So therefore it has to be ignite at 400 to 700. Still after 700, it decrease in term of weight. Okay, it does not obtain a stable mass. So it has to be ignited at about 900 degrees Celsius to form calcium oxide, which is more measurable, and mass, stable mass is obtained.